we know that 3 points define a triangle. So if I were to take 3 random points here, so let's call that point A, point B, and then let's say this is point C right over here. If we say that these 3 points are the vertices of a triangle, they define a unique triangle. So this would be triangle A. Try to draw my lines as straight as possible. Triangle A, B, C. Now, we've also learned in the last few videos that triangle ABC has a unique circumcenter. And that is a point that is equidistant to these 3 vertices. It's equidistant to these 3 points. So, the way we can find it is we draw a perpendicular bisector of each of these sides, and where the 3 perpendicular bisectors intersect, and we show that they always intersect at a unique point, that is that circumcenter. And I'll do it really quick right over here. So let's say that this is the perpendicular bisector of that side. This is the perpendicular bisector of that side. And this is the perpendicular bisector. I want to go from this is the perpendicular bisector of that side. So these are all perpendicular. This is perpendicular. And they each bisect the sides. So this side, B to this point, is going to be equal to this point to A. A to this point is going to be equal to that point to C. C to this point is going to be equal to that point to B. And this point right over here, we've already talked about. We'll call that point O. We call that the circumcenter. O is circumcenter. Circumcenter. This is all a little bit of review. So if you have 3 points, you have a unique triangle. That unique triangle has a unique circumcenter, which is equidistant to the 3 points of the triangle. The 3 vertices of the triangle. And that distance between the circumcenter and the 3 points, the 3 vertices, I should say. So let me draw that in a different color. So this distance, OA, the length of OA, the length of OC, and the length of OB. So OA is equal to OC is equal to OB, which is the circumradius. Circumradius. And we've learned when we first talked about circles, if you give me a point, and if we find the locus of all points that are equidistant from that point, then that is a circle. And when I say locus, all I means the set of all points. If you give me any point, right over here, so that's an arbitrary point, and you also specify a radius, and you say what is the set of all the points on this 2-dimensional plane that are equidistant, that are that radius away from the center, it uniquely defines a circle. That's how we defined a circle right over here. And similarly, if you say, look, if you start with the center at O and you say all of the points that are the circumradius away from O, it will uniquely identify a circle, and that circle will contain the points A, B, and C, because those are the circumradius away from O. So they are included in that set. So the circle would look something like, let me draw it. It would look something like this. Try my best to draw it just like that. Now, everything we talked about just now in the last few minutes is all a review. We know all of this, but I went over it just to kind of reinstate a pretty interesting idea. That if you give me 3 points, that defines a unique triangle. And if you have a unique triangle, and let me make it clear. This is 3 non-collinear points. So 3 points not on the same line. If you have 3 points that are not on the same line, that defines a unique triangle. For any unique triangle, you have a unique circumcenter, and circumradius. I'll rewrite it. I don't want to get lazy, confuse you. Circumradius. And if you give me any point in space, any unique point, and a radius, the set of all points that are exactly that radius away from it, that defines a unique circle. That defines a unique circle. So we went through all of this business of talking about the unique triangle and the unique circumcenter and the unique radius to really just show you that if you give me any 3 points, if you give me any 3 points, that eventually really just defines a unique circle. So just as you need 3 points to define a triangle, you also need 3 points to define a circle. 2 points won't do it. And one way to think about it is if you give me 2 points, there's an infinite number of triangles that I construct with those 2 points, because I can put the third point anywhere. I could construct this triangle. I could construct this triangle. I could construct this triangle. I can construct this triangle. And all of these triangles are going to have different circumcenters and different radiuses, and so they're going to have different circles that circumscribe about those triangles. So this one, for example, this would be one circle that could go around, that could circumscribe that triangle. You could have this circle right over here. So you see clearly, very clearly, that 2 points are not enough. You need 3 points. 3 points lead to a triangle. You lead to a unique circle. So that by itself is kind of cool. Now another question is if I have just a circle, and if it's circumscribed about an arbitrary triangle, is the center of that circle necessarily the circumcenter? So let's think about that a little bit, because there are some, I guess, unnatural, or I wouldn't say unnatural, non-intuitive cases here. So if I draw a circle right over here, its center is right over there. And if I draw an arbitrary triangle where all of the vertices of that triangle are on this circle, is this center necessarily the circumcenter of that triangle? So let me draw a crazy situation. So let me draw one where this thing is clearly outside of the triangle. So that we could have a triangle that looks like this. And it's clearly all 3 vertices sit on the circle. So you might at first say, wait, there's no way this could be the circumcenter. It's not even inside the triangle. But remember, this point right here is equidistant to every point on the circle. I should say every point on this circle is equidistant from this point. They are all the radius away. And all 3 points of this triangle are on the circle, so they are all exactly a radius away from this point right over here. So this distance right over here is going to be a radius. This distance right over here is going to be a radius. And this distance right over here is going to be a radius. Now, this point is clearly equidistant from that point and that point. We know that. It's exactly r away from both of those vertices of the triangle. So if it's equidistant, and we proved this in a previous video, if it's equidistant from both of those points, it must be on the perpendicular bisector of the segment that joins those 2 points. So this must be on the perpendicular bisector. So it's perpendicular, and it bisects that segment right over there. But we can make the same argument for this segment right over here, because this point is r from the center. We'll call it O. I'm tired of just saying this point. Point O is equidistant from, let me label these. So let's call this A, B, C. So we already said point O is equidistant from C and B, so it must be on the perpendicular bisector of BC. And it's also equidistant from A and B. It's r away from both, because A and B both sit on the circle. They're both a radius away from the center. So it also must sit on the perpendicular bisector of AB. So it also must sit on the perpendicular. That doesn't look as, that didn't, let me draw it a little bit neater. There you go. So it must also be on this perpendicular bisector. And then finally, it also is equidistant from A. It's for the same distance from A as it is from C. Because those are both r away, they both sit on the circle. So it must be on the perpendicular bisector of AC as well. So AC is right over here. And this is what the interesting thing is. We're seeing that the three perpendicular bisectors of the 3 sides of this triangle, they do definitely intersect, but they're intersecting at a point outside of that circle, outside of that triangle. And that point is the center of this circle. So once again, the last point, right, the last idea is O is equidistant from A and C, so it must sit on the perpendicular bisector of AC, which would look something like this, which would look something like that. So once again, we see the 3 perpendicular bisectors are intersecting at a unique point, and O really is the circumcenter. So if you take any circle, if you take a circle and if you put any triangle whose vertices sit on the circle, the center of that circle is its circumcenter. So we just drew a situation where this is a circumcenter that sits outside of the triangle proper. So point O is also going to be the circumcenter of this triangle. of this triangle right over here. And point O is also going to be the circumcenter of this triangle right over here. It's going to sit on all three perpendicular bisectors of this, and we know that because it's equidistant from all 3 points of any of these triangles where the vertices sit on the circle itself.